Let's start with the discussion of the motion in a straight line. Okay. First, let's discuss the few basic definitions of the terms that we are going to use. Okay, namely distance, displacement, and position. Let's understand these basic things first. Okay. So if we are discussing about motion in a straight line, where a particle goes along a straight line, okay, let's say it's moving along x-axis. Okay. Now we take the reference as x is equal to 0. Now the position of the particle can be anything depending on where it is on the x-axis. Now for example, let's say if the particle is 2 units to the right of the reference point, which is x is equal to 0, then we call that position as x is equal to 2 plus 2. If the same particle, okay, or the object that's moving on the x-axis, if it's 2 units to the left, then its position is said to be minus 2. So here, in one case, when it's to the right of the reference point, its position is said to be plus. In the other case, when it is to the left of the reference point, it is minus. This plus or minus indicates that it's present on the either sides of that reference point, which is x is equal to 0. So this is how we indicate the position. So position tells where the particle is present, okay, with respect to some reference position. Generally, origin is taken to be the reference position, whether the body is moving along a straight line or in a plane or in 3D space. Then how do we define the displacement and distance of the particle? So the calculation of the displacement is quite simple. Okay, so displacement, mathematically we write, okay, x2 minus x1, which is nothing but the change in position. This is change in position, where I am representing x2 for the final position of the particle and x1 is the initial position of the particle. Okay, so let's say we have been observing a body in a particular interval of time. So at the start of the interval, if it's at position x1 is its initial position and x2 is its final position. x2 minus x1 would be the change in position of the particle, which is the displacement. So displacement, what basically tells us is, let's say, to understand it, let's take a simple example. Let's say a particle was initially at x is equal to plus 2 and finally it's at x is equal to minus 3. So the displacement in this particular case, I mean, if we calculate, it comes out as final position minus initial position, which is equal to minus 5 units. Those units could be anything, okay, depending on the units of length that we choose. So what does this 5 units basically represent? This minus 5 basically tells that, okay, so initially the particle has started at one position, finally it has ended at a position which is 5 units from the initial position, and that final position is to the left of the initial position. Okay, the minus represents final position is to the left of initial position. The same particle, if it has gone from, let's say, x is equal to minus 3, okay, at the start of some interval it was at x is equal to minus 3, and at the end of some interval, let's say it is finally at x is equal to plus 2, then in this particular case the displacement of that particular particle is said to be final position minus initial position, which is equal to 2 plus 3, which is equal to plus 5. Now we got the displacement as 5 units, plus 5 basically. So what that plus indicates is that the final position of the particle is to the right of the initial position, and then how far is that final position from the initial position? 5 units. So basically, if you start at x is equal to minus 3 and travel a 5 units to the right, okay, plus indicating right, 5 indicating 5 units to travel in the right, we would end up at its final position. So the displacement, when we calculate, we only consider how far the final position is with respect to the initial position, how far and in what direction it's present. So the displacement doesn't basically tell us about its actual motion between those two initial and final positions. Okay. Now we define the next quantity, which is distance. Okay. So just a minute. Just a minute. Okay. Now let's discuss about the distance traveled by a body. So how do we basically define distance traveled by a body? So the distance, we can also call it as path length. So it basically tells us the total length of the path that has actually been covered by the particle. So let's take a simple case to understand what we mean by distance traveled. Again, let's take the x-axis along which the particle has been moving. Let's say the particle was at position -3 initially, and after some time, okay, first it went from -3 to +2. Then let's say it came back to x is equal to -1. Okay. Now if we see, first it went from x is equal to -3 to 2, and then it came back from x is equal to 2 to -1. So in this case, what would be the total length of the path that has been covered by the particle? First, when it was going from -3 to 2, it travels a total length of 5 units. So in the right direction, but when we are defining the distance, the direction of the motion doesn't actually matter to us. What matters to us is the length of the path that has been covered by the particle. And then when it goes from x is equal to 2 to x is equal to -1, it covers a total of 3 units. Okay. I've been referring to the units. The units could be anything depending on the choice of the length that we make, either meters, centimeter or kilometer. So in this example now, the total distance covered by the particle would be equal to 8 units. Okay. So the distance gives us what length it has actually covered during a particular interval of time. But what does displacement give us? The displacement gives us how far is the final position of a particle with reference to its initial position and in what direction. Okay. So in this case, okay, if we again try to calculate the displacement in the same example, okay, displacement would be final position during that interval is -1 minus initial position, which is -3, which will come out as -1 plus 3, which is equal to 2 units. So as we observe, the distance traveled in this case is 8 units, but whereas the displacement is 2 units. So definitely distance is not equal to displacement. Okay. So if we do a clear, okay, thinking about this difference between distance and displacement, distance will be equal to the displacement magnitude. So why I'm using the word magnitude of the displacement is, as we have observed in the previous example, the displacement could either be positive or negative. The positive or negative tells us the sense of direction of its motion overall during the time interval of the motion. Okay. So that's why we said the magnitude of the displacement, indicating only the numerical value of displacement without any sign. So distance will be equal to magnitude of displacement only when the direction of motion does not change. That means if the particle keeps moving in the same direction without changing its direction. Okay. In any other case, the distance and displacement will not be equal. Okay. So if the direction of the motion changes, definitely in that case, distance would be less than magnitude of displacement. When direction changes. Okay. So put together both of them, we can basically write the distance, okay, less than or equal to the magnitude of displacement depending on the situation that we have. Okay. Now, so we have described these things. Now let's proceed to the next physical quantities. So the velocity and acceleration. Okay. So once we discuss about those physical quantities, then we will try to understand the relations between these different physical quantities and also try to understand the graphical representation of distance, displacement, velocity and acceleration. Okay. So now, how do we define the first let's define something called average velocity and average speed. Okay. So coming to the definitions, we define average velocity is equal to displacement divided by time taken or change in position time taken. Let's say in a time interval delta t, okay, the particle went from position x1 to x2, then the displacement would be final position minus initial position, which is x2 minus x1, and the time taken to move from x1 to x2 is delta t. Or we can also say something like this. Let's say at time t1 the particle was at the position x1, at time t2 the particle was at position x2. Then when particle goes from x1 to x2, the time taken is basically t2 minus t1. In that interval of time, the displacement of the particle is basically x2 minus x1. So this is average velocity. Since the displacement has a direction, I mean it could either be positive or negative, so the average velocity that you get would also be positive or negative. Okay. See, the average velocity doesn't actually tell us about the actual velocity of the particle when it was displaced from x1 to x2. Okay, it only gives us an average of the velocity. Okay, or with what constant velocity, if it was moving, it would be able to go from x1 to x2 in the same interval of time delta t. Okay, actually the velocity might be varying in any fashion as the particle goes from x1 to x2. As you can see, the units of average velocity would be meter per second if we consider the SI unit of displacement to be meter. Now let's go with the definition of average speed. So average speed is equal to distance traveled during a time interval divided by time taken for that particular distance traveled. Okay, again the same units, meter per second. So average speed also has the same units of meter per second. The only difference is average velocity would be a vector quantity and average speed is a scalar quantity. Okay, we do not define any direction for average speed. Okay. Now let's understand the meaning of instantaneous. Okay, so instantaneous speed and instantaneous velocity. So instantaneous speed in the sense the speed of a body, okay, at a particular instant of time. Okay, so when we travel, our speed, let's say when we go from one point to another point, our speed continuously keeps changing. Okay, so at this instant of time you might be traveling at 30 km per hour. Next moment it might become 31 or 29. So it continuously changes. So instantaneous speed at this instant is 30 kilometer per hour, next moment it would be 31. Okay, or we can define it as speed of the body at a particular instant of time. So mathematically, how do we calculate this instantaneous speed of a body, provided we know how the particle has been moving, how its position has been changing, all those things. So earlier we defined average speed as instantaneous speed. So mathematically, if we consider the time interval, this delta, this okay, let's represent distance with s, time interval to be delta t. Okay, so this time interval, when it's taken to be very small, something like infinitesimally small, okay, I will represent it mathematically something like this. Okay, so when the time interval taken is very small, then in that case the average speed becomes instantaneous speed, or we can also write it something like this, d by dt of s, where s stands for distance traveled. Similarly, if we calculate average velocity of a body for a very small interval of time at this particular instant, okay, now let's say I want to calculate the instantaneous velocity at t is equal to 3 seconds, then how I practically do it mathematically is, I will consider a very small interval of time, okay, at t is equal to 3 seconds, something like this interval between 3 to, let's say, 3.00000000001 second. So this interval, in this interval of time between 3 to 3.000000001, okay, as close to 3 as possible, then we can say the time interval is very small. The time interval in this case would be this minus this. So when that time interval is very small, then the average velocity that we calculate mathematically in that small interval of time would actually approach instantaneous velocity. Or if we keep the discussion simplified, instantaneous velocity is equal to limit delta t tends to 0. This limit delta t tends to 0 is nothing but we are saying the time interval that we are taking is very small. Then change in position divided by time, or mathematically this is nothing but dx by dt. Dx stands for a very small change in position in a very small interval of time, dt, or we can say mathematically we can call it the rate of change of position. Okay, this is about the instantaneous velocity, or we can just call it as the velocity. So instantaneous velocity or velocity is a vector quantity, whereas instantaneous speed, or we can just call it as speed, is a scalar quantity. Now let's focus on acceleration. Okay, first we will define about average acceleration, then we will define about the instantaneous acceleration mathematically, similar to how we have defined the average velocity and then instantaneous velocity. Okay, see, the velocity of a body need not be the same all the time as the body is in motion. So the velocity might be increasing or decreasing. So acceleration is a term which tells us how fast the velocity is increasing with respect to time, or how fast it's decreasing with respect to time. So average acceleration during a particular interval of time is equal to change in velocity during that interval divided by time taken for that particular change. Let's say at a time t1, okay, when we started observing the motion of the particle, the velocity of the particle was v1, and at another time t2, the velocity of the particle is given by v2. Then we have been observing the motion of the body in that time interval between t1 to t2. Okay, then the time interval during which we have made the observation is t2 minus t1. So for that amount of time we have been observing the body. So during that interval the velocity changes from v1 to v2. Then average acceleration would be v2 minus v1. So the velocity in that interval has changed from v1 to v2, and it could change in any way, in any random way. So but what we are interested here, regarding the average acceleration, is that, so when we calculate average acceleration with this particular relation, okay, it gives us the value of some constant acceleration which would change the velocity of the body by the same value in the same interval of time if the body had such a constant acceleration. Now as you can see from here, average acceleration, the units would be SI units if we are talking about. Change in velocity has a units of meter per second, time has a units of second. So we would basically get meter per second square. Now if we define instantaneous acceleration again, so average acceleration calculated during a time interval becomes instantaneous acceleration if we assume the time interval to be very, 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 very small. If I want to calculate instantaneous acceleration at this instant, I consider a very small interval of time. Okay, so during which I will calculate average acceleration. It will be very close, almost so close, if we take the time interval to be very small. It will be so close to the instantaneous acceleration. So we can say limit delta t tends to 0, delta v by delta t is equal to dv by dt, or this we can call it as rate of change of velocity. So the rate of change of velocity of the body would be equal to the instantaneous acceleration, or we can just call it as acceleration. So basically instantaneous acceleration is also a vector quantity. Okay, or acceleration is also vector quantity, both instantaneous as well as average acceleration. So now we have understood the basic terminology. Let's discuss a few example problems of how these things can be used in order to frame questions. Let's take one example. Okay, let's try to understand all these things during this whatever we have discussed in this one simple example. So let's say a particle, okay, was moving along x-axis whose position varies with time, something like this: 3t square minus 4t plus 2. So here x is nothing but position of a particle which is moving at position of particle at time t. So the variation of position with time is given. So now let's try to discuss few things here. So first, let's say you wish to calculate the position of the particle, let's say at t is equal to 0. So let me call it x naught. X naught stands for the position of the particle initially. So generally whenever we say initially, that means the moment when we started observing the motion. So that is, we consider at that moment t is equal to 0. Then if I substitute t is equal to 0 there, so we would get it as 0 plus 2. So this is equal to, x naught is equal to 2 units. So at t is equal to 0, okay, the position of the particle is 2. Now let's calculate position at some other interval of time. Let's say we want to calculate at t is equal to 2. So position at t is equal to 2 is given by, just substitute t is equal to 2 in that particular relation, 2 plus 2. So which is equal to 3 into 2 square would be 4 minus 8 plus 2. 3 4s 12, 12 minus 12 plus 2, 14 minus 8, which is equal to 6 units. Okay. Now let's say we wanted to calculate displacement during interval of time. Okay. So if we want to calculate displacement, my interest is to calculate displacement in the interval, let's say 2 to 4 units. Sorry, not 2 to 4 units, in the interval 2 to 4 seconds. Okay. So let's assume in this case, for our convenience, let's say the position is expressed in meters and time is expressed in seconds. Now if we want to calculate displacement in the interval 2 to 4 seconds. The first we need to find position of the particle at t is equal to 4, and we also need to calculate position of the particle at t is equal to 2. So we have already calculated position at t is equal to 2. Let's calculate position at t is equal to 4. So position at 4 is given by, okay, let's substitute t is equal to 4 there, minus 4 into 4 plus 2, which is equal to 3 into 16 minus 4, 16 plus 2. So 32 plus 2, it would come out as 34 meters. Okay. Now if you see here, the change in position, 34 minus 6, which is equal to 28 meters. That would be the displacement during the interval 2 to 4 seconds. Now let's calculate the distance during a particular interval of time. As I told earlier, while calculating the distance, it's the total length of the path that has been taken by the particle. Okay, so the total distance traveled during an interval of time need not be equal to the displacement during the interval. It will be equal to the displacement provided the direction of the motion does not change during that time interval. So whenever calculating distance, first thing we need to check is if the velocity was changing its direction during a particular interval. Okay, so to find distance, okay, we need to understand about the direction of motion of the body. So to understand that, let's calculate the velocity first, then we will proceed with the distance calculation. First, let us try to calculate average velocity during a interval of time. Let's say we wanted to calculate average velocity between t is equal to 2 to 4. So average velocity is nothing but displacement during that interval divided by time taken, which is 4 minus 2. We already calculated the displacement between t is equal to 2 to t is equal to 4, which is 28 divided by 2, which is equal to 14 meter per second. That would be the average velocity. So what this average velocity represents is that if you were traveling with a constant velocity of 14 meter per second during that 2-second time interval, your displacement would be 28 meters, same as in that interval of time. It doesn't mean that you are actually traveling at 14. It doesn't mean that the particle described in this particular example is moving with that constant velocity. Okay. Now let's calculate instantaneous velocity of the particle. Okay. Since we know that x is equal to 3t square minus 4t plus 2, so x is given by 3t square minus 4t plus 2. Let's calculate instantaneous velocity. So instantaneous velocity, or I can just write it as v, is equal to the rate of change of position of that particular particle. So d by dt of 3t square minus 4t plus 2, which is equal to, so we would get 3 into, okay, since you already know the basic differentiation, I'll write it directly, 6t minus 4. So at any time t, the velocity is given by 60 minus 4. Okay, so 60 minus 4 is the velocity at a time t. So if you observe properly in this particular case, the velocity is changing with time. It's not constant. So we can say that the motion of this particular body is non-uniform motion. Motion is said to be uniform motion when velocity is constant or it doesn't change with time. It is said to be non-uniform motion when velocity changes with time. So we have another term called uniform and non-uniform acceleration. Just 1 minute. This motion is non-uniform motion. Then, okay, when do we say that body is uniformly accelerated? It is said to be uniformly accelerated when acceleration of the body is constant or does not change with time. So to conclude, in this case, whether acceleration is uniform or non-uniform, let's calculate acceleration of the particle. So which is mathematically the rate of change of velocity or time rate of change of velocity. Okay, at what rate it changes with respect to time. 60 minus 4. If we differentiate this with respect to time, we'll get it as 6 meter per second square. As you see, the acceleration is not dependent on time. So it's independent of time, which means it doesn't change with time. So as the particle moves at any instant of time, the acceleration is constant. So in this case, since a is equal to 6, okay, so we can say the particle or the body is moving with uniform acceleration, or we can say the motion corresponding to it is a uniformly accelerated motion. Okay, now let's try to calculate the distance in a particular interval of time. Okay, before that, to discuss a problem on distance, let's try to understand, okay, at what time the velocity of the particle becomes 0. Now we wanted to find, let's say the question was something like this: at what time velocity of particle is 0. So this is what they asked us to find. Then in order to find the time, so we already know that at some time the v is 0. Now we wish to find that time, so we'll express v in terms of t. We get 60 minus 4 is equal to 0, or 60 is equal to 4, or t is equal to, we would get 4 by 6, which is equal to 2 by 3 seconds. So basically at t is equal to 2 by 3 seconds, the velocity was 0. Okay, now if you make one proper observation that at a time, just observe the velocity properly. Just 1 second, let me scroll down. So we have x is equal to 3t square minus 4t plus 2. So if we observe properly, 1 minute, 4t plus 2, velocity is equal to 60 minus 4, and acceleration is equal to 6, and velocity is equal to 0 at t is equal to 2 by 3 seconds. So if we make one observation, when t is less than 2 by 3, okay, velocity is negative. Just check there. Okay, if we use this condition, 60 minus 4 less than 0, we will get t less than 2 by 3. That means when t is less than 2 by 3 seconds, velocity is basically negative. That means initially the particle was moving, okay, 1 minute, this is v. So initially v is less than 0 for the time less than 2 by 3 seconds. That means between 0 to 2 by 3 seconds, the particle, it was moving in left direction, or we can say as the particle is moving along x-axis, we can say it's moving towards negative x-axis. And if you make again observation, if we use this condition, v greater than 0, and you solve this, 60 minus 4 greater than 0, we'll get 60 greater than 4, or t greater than 2 by 3. That means for time greater than 2 by 3 seconds, velocity is 0. That means after 2 by 3 seconds, or when time beyond 2 by 3 seconds, the body velocity is greater than 0, means positive. That means it's moving in right direction. So this is the conclusion that we can make. Okay, so just make one, let's take a x-axis to understand this better. So we already calculated the position of the particle at t is equal to 0, and we got it as x is equal to 2. So at t is equal to 0, the particle was at x is equal to 2, and it started moving in the left direction until 2 by 3 seconds. At 2 by 3 seconds, velocity became 0, and then it started to move in the right direction. So let me try to calculate its position at 2 by 3. So x2 by 3 would be 3 into 2 by 3 whole square minus 4 into 2 by 3 plus 2. So this would come out as 4 by 3 minus 8 by 3 plus 6. So this would come out as, what would this be equal to? Minus 4 plus 18, which is nothing but, just a minute. So are we doing it correct here? Minus 8 by 3, 6 3 is 18, 18 minus 4, which is nothing but 3 into t square minus 4 into t. Just 1 second. I made a small mistake here. This is supposed to be 2, not 6. Then we would get it as minus 4 by 3 plus 2, which would be 2 by 3. So it would move in the left direction until 2 by 3 units. Okay, this is x is equal to 0. So it would move only until here. Okay. Then after that, okay, again it would start to move in the right direction. Okay. Now we have understood the motion of the particle. Okay. Now let's say they framed a question something like this. They wanted us to find the displacement of the particle between 0 to 1 second. In the interval 0 to 1, we want to find displacement. Clearly, in that interval 0 to 1, displacement magnitude will not be equal to the distance traveled, because as you see, between 0 to 1 second we have 2 by 3. 2 by 3 lies in the interval 0 to 1. So at t is equal to 2 by 3 seconds, the direction of motion is changing, hence the displacement will not be equal to distance. So how to calculate distance in the interval 0 to 1? So what we do here, first we have to calculate distance in the interval 0 to 1. So let's break it apart into pieces. First let's focus on the interval 0 to 2 by 3. So 0 to 2 by 3, there is no change in direction of motion. So the distance traveled in this interval is equal to the magnitude of displacement. Let's call it S1. And then from 2 by 3 to 1 second. So between 2 by 3 to 1 second, the body is always moving in the right direction because it has a positive velocity. So in that interval also, direction of motion is not changing. Let's say distance traveled in that interval is S2, which would be equal to the magnitude of displacement during that interval. So what would be the displacement in this interval? So position at 2 by 3 seconds, which is final position, minus position at this time, minus initial position, which is at t is equal to 0, which is nothing but 2 units, which is minus 4 by 3 displacement. So the distance traveled S1 would be equal to 4 by 3 in that interval. Now let's calculate displacement in the interval 2 by 3 to 1, which would be the distance traveled in that time. So first, displacement between t is equal to 2 by 3 to t is equal to 1 is nothing but position at 1 minus position at 2 by 3. So the position at 1 is given by 3 into 1 square minus 4 into 1 plus 2, which is equal to 5 minus 4, 1. So 1 minus 2 by 3, which will come out as 1 by 3. So this would be equal to the distance traveled in that interval. So the total distance traveled in the interval, okay, distance traveled in the interval 0 to 1 second would be nothing but distance traveled between 0 to 2 by 3 and 2 by 3 to 1. So what we have basically done in this particular example is, so first we identified the time at which the motion direction changes, and we broke the problem into pieces such that in each piece the direction of motion does not change. And we know that when direction of motion does not change during a particular interval, the distance traveled would be equal to the magnitude of displacement. That's what I have used. Okay, now let's do one more simple problem here. Now let's say they asked us to find speed at some instant, let's say t is equal to 2 seconds. Okay, so one small fact, the speed at any instant of time will be nothing but magnitude of velocity at that particular instant. So we already got the velocity. We got the velocity as 60 minus 4. So what would be the velocity at t is equal to 2? 6 into 2 minus 4. 6 to 12 minus 4, which is equal to 8. So the speed at t is equal to 2 seconds would be 8 meter per second. Okay. Speed has only magnitude. So 8 meter per second is nothing but at that instant it's moving such that the rate at which its length traveled changes is 8 meter per second at that instant. Now the velocity that we calculated here came out as plus 8 meter per second. This plus indicates that at that moment the particle was traveling in the positive x direction, or it was moving towards positive x direction. Okay. Now, so I hope you understood the basics of all basic definitions of the physical quantities and got a bit of idea of how to use them in the problems. In the next lecture, we'll discuss about the graphical way of understanding these physical quantities and how questions can be framed graphically. Okay. We'll meet in the next lecture again.